Okay, computer architecture. What is computer architecture? Let's move back a little bit. What is computer science? What is computer engineering? We have a major called computer science. So we call this department computer science department. Computer. Would somebody tell me what computer has to do with? What fields, what majors computer science or a design of a computer has to do? Chinese literature?
No.
Maybe. Don't say no. Never say no. What other majors we should pay special attention to when we call ourselves computer scientists? Electronics, definitely. If you don't understand electronics, then you don't know what megahertz means. You don't know why we cannot crank up the clock rate. If you don't know electronics, you don't know why we have so many transistors available today on a chip, on a blade, or even in a rack. Then you don't know how to construct large-scale systems. If we don't understand electronics, we don't understand communications, then we don't understand Internet. We don't understand why cloud computing is so hot these days. Okay, if we don't understand electronics, we don't know why the top 500 supercomputers are mostly vector computers in 2 decades ago, and maybe clusters in a decade ago. And these days, the form of the computers change again. Okay, what other majors? What are the most related majors?
For example, formal languages and theory, modeling.
Formal language department? Never heard of that. So, grammar. Language. How can we make computer language? When I say computer language, I refer to high-level programming languages. Can be so friendly, easily usable to human beings. Can you design a language which is very natural to human beings and very compilable to machine code? That's very important. How do you construct the program? How do you construct the data structures? How do you orchestrate all the hardware and software to finish the job for you? And when facing different types of questions, problems like large-scale data parallel problems, what kind of language, statement structures, instructions, operations can be suitable? Or maybe it's not scientific data parallel type problems. It could be thread parallel, task parallel. Like this system is going to deal with thousands of users. Everyone has different requests. Wants the computer system to do different calculation for him or her. What kind of computer, like operating system, task scheduler should be capable of to face such a situation? Okay, so language is important, and this language traces back to human language. because eventually the users will be us. Okay? We use the computer. If we think it's easy to use, then this is a good design. So even language, I would say yes. How many languages do you know? What's your mother tongue? And yours? And yours? And yours? Human beings have all kinds of different languages because of the cultural differences and because of the geographical divisions. Okay, maybe these people never talked to the other people for thousands of years, so they developed different natural languages. But all the purposes of the human languages are the same. How do you call your mom in your mother tongue? Mom. How do you call your mom in your mother tongue? Ma. That's weird. Every human language calls mommy about the same. But anyway, there are reasons for us to use different languages. But for the computer, all the computers are English-based. So all the computer high-level programming languages should be the same. Tell me, that's right or not? Is it right? Of course not. We have Java, we have C. They both are C-based. Anyway, we have Fortran, we have COBOL, we have like internet programming language, network programming language, web page programming language, all kinds of programming languages. How come we have so many languages? Even we already know the computers are all English-based. Why? Okay, this time it's because the purposes of every language is different. It's not like the human languages. All the human language purposes are the same. But for the computers, all the languages are different. So how many languages do you master? Right, how many languages are you good at? Just one? Okay, you can drop the course. Don't even tell people you're our student. You lose our face. It's just like a mechanic. The car repairman can use only wrench, but nothing else. Don't even know there's something called a screwdriver. You think he can make a good mechanic? No way. So if you know only one type of language, or if you know only one single language, whatever problem is given to you, you always use that language to write your programs, you're already a dead man in our field. Okay, so language has a lot to do. So whenever there's a new need, we may have to design a new language for it. Okay, what else? What are the majors? Mathematics. Of course, that's the number one answer. Computer comes from computing, and when you want to compute something, you have to know all the integrations, differentiations, whatever, all kinds of mathematics. So, are you good at mathematics? No. Okay, you can drop the course too. So mathematics is so important that you have to refresh your memory, refresh whatever you learned in high school in your undergraduate courses. Otherwise, don't tell me you can write good programs unless the program is too trivial. Okay, so mathematics is so important that I cannot emphasize anymore. What other fields do you think is important? Communications, of course. Computer is already pervasive in communications. Right now, whenever you take a phone out, the first thing you'll face is A to D conversion.
I mean the buses and serial ports, those.
I haven't gotten to there yet. Okay, once it's digitized, all the digital information will go through everything you can think of, buses, processing, filtering, high pass, low pass, whatever, are all translated into the digital form. Maxwell equations performed in the digital form. Fourier transform, have you heard of that? In digital form. So we have digital processing course, digital signal processing course, a very important course in our department. All of these are based on EE, on communications theories. Okay, what else?
Psychology.
Because users are human beings.
Facebook.
Because of Facebook? Never mention any trademark. Never mention any product name in this classroom. You may drop the course the second time now. Because of the social network, say that social network. Okay, because of all the relational processing. Okay, and also material science, chemistry, quantum mechanics, photonics, many things that you need to understand. Okay, semiconductor in EE, very important for our memory system construction. Okay, we used to talk about binary, everything is binary, even memory is binary, but now we have tri-state memory cell, electronic cell, multi-level, fresh bit storage. That's electronic. And the fresh memory is semiconductor in nature. But how come when we unplug it, when there's no power supply at all, the information can retain? For 10 years, at least 3 years. How come? What you have learned is, if that's semiconductor memory, whenever you unplug the power, everything goes away, right? But this time, things change. How did you make that possible? Do you know why? If you don't know why, it's just like if you're majoring in automobile engineering, but you cannot tell the difference between a diesel engine and a gasoline engine. Okay, now come back to the CPU design. CPU, central processing unit. How many types of CPUs? Do you know? How many types of CPUs? Don't tell me there's only one kind. Even for gasoline engine, we still have 1 cylinder, 2 cylinder, 3 cylinder, 4, 5, 6. For 6, we have inline engine, okay, or V-type. And for the V-type, the angle matters a lot. How many degrees? Or it doesn't matter? And Subaru makes the angle 180, making it horizontal engine placement. What degree is the perfect angle? 90 degrees. Nothing is perfect. And everything depends. So for the engineering problems, never tell me this is the truth. Engineering, why do we call that engineering, don't call that science? Do you know why? Because there's no truth. And we only want to solve problems. And how to solve problem based on what our knowledge is and what our technology is, okay? So the solution today may not be suitable tomorrow and cannot be implemented yesterday. Okay, so for the engineering problem, there's always one current solution. And for the current solution, you may say this is perfect for right now, but maybe not for the next minute. That's why we call it engineering. Engineers always can solve problems quickly and efficiently, but never need to care too much about where the optimal solution is, where the truth is. Okay, so we're somewhat different from the scientists. Okay, so much about this. How many types of CPU do you know of? Nobody wants to answer this question? Then I can only refer the question to our TAs, right? Agree? Agree? Okay, being a TA is not that easy. TAs tell me, how many kinds of CPUs do you have? Do you know?
I think at least we have 2 types of CPU.
One is Intel and the other is AMD. No brand names.
General purpose and special purpose.
Okay, very lousy answer because special purpose is what? How do you classify or define the term general purpose? But that's the answer we're using currently. Why? Because we're only engineers. Okay, general purpose. What do you mean by general purpose? That's the collection of applications among which you are unable to point out any special feature in these applications. Okay, no special characteristics can be found in the set of programs. If that's the case, then we call that general purpose applications. Okay, so whenever you say general purpose application, you must put an S in the back. There must be a lot of applications in order to be able to be called general purpose. Now back to the other type, special purpose. How many special purpose types do you know of? Vector, media, streaming, voice, video, graphics, whatever, all kinds. Or even for real-time applications for system control. So we have yet another type called microcontrol unit. What is a microcontrol unit? It's a very simple CPU, can handle only limited tasks, but will have to respond very fast. How do you describe very fast? We usually use the term real time. What does real time mean? Well, as long as it's fast enough to interact with the user, whatever that user is, another computer or a human being, doesn't matter. As long as the response time is fast enough, then we call it real time. Okay, so real time doesn't have a numeric definition. It's just the scenario. Okay, so real-time scheduler. In the real-time OS, the only key research topic is scheduler. How can the scheduler, when facing some existing tasks and incoming tasks, reschedule these tasks to satisfy all kinds of real-time requirements by different tasks? That's the only key research issue in real-time OS. Okay, very simple, only one single point, but this becomes a field, becomes a few courses for you to take. Okay, so now you understand CPU a little bit. Is CPU enough? No, there are still memory and I/O. What is memory? Oh, a lot of things in it. cache memory, main memory, secondary memory. The secondary memory can be flash, can be magnetic disk, can be tape. What if we have all three? Or if we have two? Which one should be placed at the upper level? Which one should be placed at the lower level? And for you, for most of you, the disk capacity is already huge, right? Is the disk capacity huge to you? Then why bother to use tape? There comes the next question. What about the tape storage capacity compared with the disk? Comparable?
Much bigger.
Why? How come?
Because it doesn't have speed requirements.
Doesn't have speed requirement, then how come we cannot design a disk without speed requirement and say, hey, that can also store that much information in it? That's just yet another kind of disk, so that we can save one hardware device. So what's the difference in nature between disk and tape? How do you know? Why do we need to have tapes? Somebody tell me that.
Backup.
What?
Backup of the data.
I know, but why don't you use disk to do backup? You think tape is safer? It's also magnetic based, still the magnetic coating. And the disk is magnetic coated. What's the difference? So don't think I cannot recognize you when you put on a different clothes.
Less power consumption.
Less power consumption. Long time back, we don't care about power consumption in computer design. It happens only recently.
Maybe it can last longer on the tape, like not 3 years, but maybe longer.
Oh, I wouldn't say so. You see, on the disk platter, I coat magnetic material on it. This platter usually won't be bent. But on a tape, it's not so safe. Okay? So when you say last longer, that may be because you use it less often. But if you use it similarly often, then maybe a disk is a better storage with better permanence. So why do we need to use a tape in addition to disk?
Size.
Size, this is disk, this is tape. Have you seen micro tape?
Yeah, the capacity size, physical size and storage size together.
Right, that's my question. But that's not the answer to that question. And what did you say?
No, the same. The storage.
Oh, the same stupid answer, right? So why? Why? The answer is so obvious. The answer is the surface area. So for disk, you have only so much area to put information on. But for tape, when you accumulate, aggregate the area of the tape, you know how huge the area is. Okay? So much area to put information on, yet it can be stored in such a compact space. Now, do you know why? Okay, so one tape of this size, one disk of this size, the magnetized surface area ratio could be 1,000 to 1, or even more than that. Now, do you know why we need to have tapes? Museum archiving, all kinds of things must be put on a tape. No, there's nothing that's must. Can be put on such a tape, or could be put on a room full of disks. Which one do you prefer? Now you understand why we need to have tapes. Very important storage medium. I/O. Serial, parallel. Is serial communication faster than parallel? Or the other way around? When you have 32 wires transmitting a word in one clock cycle, suppose it's synchronized. Or if you have only one single wire, every clock cycle you can transmit only one bit. Tell me which type is faster? Parallel? Wrong answer. Somebody want to give me another guess? Because if it's implemented in a die on silicon, when you have so many wires, it doesn't have to be so many. Let me use 2 wires, for example. If you have 2 wires, then the coupling capacitance needs to be charged, discharged every time you want to transmit. So the capacitance drags the transmission. The speed becomes extremely slow compared with only one single wire without any coupling capacitance. So on a die, we prefer to use only one single wire for high-speed transmission. Without double E background, you won't understand that. Okay? When it comes to the PC board size, then maybe 32 is much faster. Okay? But that also depends. When you crank the clock up to megahertz, coupling capacitance effect becomes serious, very severe. Slowdown factor begin to appear. Okay. So learning how to design computer right is a very interesting thing. And there's a lot of background knowledge that you need to have. Pay more attention to the relationships between this course and other courses. Next thing I like to talk about is compilation, compiler. Why does compiler have to do with computer architecture?
Optimizes the machine code that is created by your language.
Okay, because compiler can be categorized as a piece of software, right? But this piece of software is very different from the others. The compiler directly determines how the hardware should be used. The commands, the requirements come from the high-level language program. And the resources it has in its hand are all the different kinds of hardware, including caches, level 1, 2, 3, instruction cache, data cache, whatever, including I/O, including your ALU, how many ALU, what types of ALU you have, how many registers you have, how to use these registers, are they enough, including what kind of operations you have, move, load, store, including software system function call. Whenever you make system function call, what is the cost? Or you rather write a subroutine to implement it using your own machine code. So compiler is so closely related to computer architecture. It's back to back, stuck together. So if you want to really learn this course well, you have to fully understand compiler. What if the machine's pipelined? What if it's not pipelined? What if it has these kind of instructions? What if it doesn't have this kind of instructions? The high-level language doesn't matter much here, okay? It's all translated into requirements only. Okay, in whatever form, I don't care, but as long as I know what you want, then I implement it for you on hardware. Okay, so that's compiler. What about OS? Somebody tell me the OS, how it relates to computer architecture. Looks like you like to give a try.
Yeah, make it possible like software application or software users to communicate with the hardware.
Only to communicate? So the OS is like a phone booth. You can go in there and dial to talk to somebody else.
It manages memory, schedules.
Okay.
Resource allocation.
Okay. Okay.
But the operating system manages the resources, hardware resources.
Okay. So the OS is the big boss. It's the god. Everything is under its control. It even determines whether you can edit a new program or not, right? Because you want to use the editor. And even if you want to submit that program for compilation, it determines when you can do that. Okay? And it asks you what level optimization you want in your compilation. So you choose level 2, but maybe you can override your wish and say, level 2 is not appropriate for you at this moment. I'll compile it using a different level. Okay, so OS controls everything, determines everything, knows everything. Next question is, do you want to have an OS in your system? You do? Okay, lazy guy. And your answer, do you want to have an OS in your system? You do? Or you want Microsoft to make money from you? Okay, so a real expert wouldn't want to have an OS unless he thinks this part is not important. I'll leave it to you. I don't care. But a real expert will rather do the management by his own, on his own, or on her own. Do you think so? So do you want to have a manager in your home so that after 2 weeks you don't even know where your slipper, your coat, your toothbrush is? You don't know everything. You have to ask your house manager, hey, I like to brush my teeth. Tell me or bring me my toothbrush. You want to have such a house manager?
Well, maybe yes.
Well, that depends. Depends on how huge a house you have, and depends on how busy you are. It is said that if there's a $100 US bill on the ground when Bill Gates passes by, he better don't pick it up, because if he wants to pick it up, that will spend him how many seconds? And if he uses this time to run his business, he can make a lot more than $100 US. Have you heard of that joke? So you want to have the house manager? That all depends. But for a student, for a scientist, at least you should be able to live without it. You should be able to do it on your own. And you should know what things you want to leave to the OS, what things you want to keep in your own hand. Okay? So back to our previous question. How does computer architecture have to do with OS? Much? Not much? Whatever hardware system I have, I just take any arbitrary OS and put it on and it runs well? Impossible. So what's the relationship between OS and computer architecture?
Designed for the architecture.
Becoming curious? Well, we don't have that much time. we need to go back to our course material. So now you already understand how important, what kind of a role computer architecture has in computer science. Without understanding the machine itself, then simply being able to program, you're not any better than students in other majors. In our university, NCTU, every department teaches computer science introduction to computer science. Every department teaches programming languages. Okay, everybody can use C language, C++ to write programs. So writing program, all the high-level languages are for people from 8 to 80. Not for the specialists, not for us pros. We need to be able to design such languages for them. Design machines to run the language, to run the programs written in this language as well. Okay, and compete on the stage with all the researchers, designers from everywhere in the world, especially those from Korea. Watch out for Koreans. Okay, we talked about exams. We talked about the term project plus the presentation. In the presentation, you need only to turn in the FOIL file to me. You don't need to have a report written up for me. Just the FOILs will be sufficient. Okay, but in the FOIL, you need to have information like, what is my topic? That's for sure. Why do I choose this topic? And what's the current status of the research work on this topic? Okay, and then you can do different things. First, you can do paper study only. Read all the papers about this topic. Don't just read a single one paper and present. Read a series of papers about this topic. That's called survey type presentation. Or you can do some design. In your design, you don't need to know all the existing design techniques, but at least you need to know the basic design concepts. Okay, I would not require you to know everything like, something has just published yesterday in what conference, so you get a 0. I won't be so mean. Maybe you need to know the like 50% of the current status. That'll be sufficient to me. Some too advanced topic you don't need to know. Okay, and then do your own design, because after all, you're just taking a course. You're just a student. Design, or there's a smart design, and the designer claims that this design is superb, but he never show you how to implement this design. Then you can try to implement it. Sometimes a very good idea is not realistic. And when you really implement something, there will be overhead. Okay? Or there will be oversimplified assumption in his design. So when you really want to implement it, like the data is always available, but in fact, the internet gets blocked from time to time. So your input cannot be so smooth. So maybe he said, assuming the input is always available, but when you want to implement it, you found out that without a queue, it is impossible. Okay? Or you validate something which other people claim. He claims that the order of complexity of this is what, and in real implementation, you can achieve what performance level. Then you show him that in real world, the worst case can be how bad. The best case can be how good. The average case can be whatever. You may need to collect a big collection of data in order to show if this design concept is realistic or not. Okay, something like that. Okay, or you can do some physical implementation, circuits, blinking lights, whatever you can think of, and show me a physical implementation. That can also be a term project, may be interesting. But I don't want something too superficial. Let me tell you what is superficial. Do you know multimedia? Multimedia has a lot of mathematics, a lot of calculation behind it. Objects in the space. This is my viewpoint. This is my view angle. This is my view volume. This thing gets blocked by something in front of it, and this thing is semi-transparent, so the object behind it can be seen somehow. So the color will have to be blended together, mixed together. Like if I have a red here, a blue here, and both are transparent, then what will the color be? Black. Okay, so you need to do a lot of calculations, mixing, blending, whatever, and shadow, light sources. A lot of calculation transformations. Yet, long time back when we have some multimedia tools, many graduate students use those tools to do some demonstration and then get a master's degree. Have you heard of that? Okay, whenever there are visitors to our department, we ask those professors, those labs, to do demo for us, because those kind of things are very interesting, easy to show. Okay? Yet, after that graduate student gets the master's degree, that tool gets obsolete, out of date. Okay? New tools come out. And what he has learned does not have any market value. And what knowledge does he get? Nothing. Nothing. He doesn't know calculation. He doesn't know triangulation. He doesn't know mathematics. He doesn't even know why computers can do all this, where to store so many objects, how to manage these objects in the computer system, how to do calculations. Okay? So sometimes we learn new, real knowledge. Sometimes we learn some fake knowledge. All that you know is nothing but those things written in the user's manual. Like web surfing. Some people are very good at searching information on the web. You think he deserves a master's degree? Or he's nothing but a very popular student worker? Okay, so what's real knowledge you need to be able to tell? These days, we often see people on the street holding an electronic device and do something like what? See that? Or see that? How can this be sensed by the device? How to filter out those fake instructions? 2-point, multiple point control. How to identify all these points? Calculate their relationships with each other so that you understand what the user really means. Okay, all these are a lot of techniques, a lot of mathematics, electronics behind it.